Tonight, we're heading in the one direction nobody ever goes. We've sent machines to every planet, landed on Mars, flown past Pluto, and crossed the edge of the sun's bubble into interstellar space. But there is one direction we have barely touched. Not across the solar system, but straight out of it, rising clear of the flat plane the planets share, toward the unexplored space above the sun's pole, or below it. You'd think it would be simple, just aim away from the disk and fire the engine. But that trip turns out to be among the hardest we could ever attempt. By the end of tonight, you're going to understand why climbing straight up out of our solar system is harder than reaching Pluto, and what waits in those two unexplored zones above and below our star. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Look at almost any picture of the solar system, and you'll notice something that nobody ever points out. Everything is flat. The planets sit in a line, like beads strung on a wire. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all of them lined up across the page. The planets really do travel in roughly the same flat sheet, like marbles rolling around the inside of a giant invisible dinner plate. Astronomers call that sheet the ecliptic plane. It's the plane of Earth's path around the Sun, and almost everything else in the solar system hugs it closely. Mercury wanders a few degrees off it. Most of the other planets stay within a degree or two. The asteroid belt sits in it. The big moons orbit close to it. Even most of the comets that swing in from the cold outer dark tend to follow paths tilted only modestly away from it. So when you imagine the solar system, you should not imagine a sphere with objects scattered all around it. You should imagine a disk. A wide, thin, spinning disk, with our star burning at the center, and everything we have ever visited skating around inside that disk, like figures on a frozen pond. You might be wondering why this should be true at all. Why should a star and its planets bother to arrange themselves into a flat sheet? Why not a sphere, with worlds scattered in every direction, some over the top, some underneath, some out to the sides? The answer takes us back to the very beginning, to the moment our solar system was born. Roughly 4.5 billion years ago, there was no sun and there were no planets. There was only a vast, cold cloud of gas and dust, drifting in space, the leftover material of older stars that had lived and ended long before. That cloud was enormous, stretching across distances we can barely picture, and it was thin and quiet and slowly turning. Then, something disturbed it. Perhaps the shock wave from a nearby exploding star rolled through and squeezed it. Whatever the trigger, one region of that cloud began to collapse under its own gravity. As it collapsed, it pulled inward on itself, growing denser and hotter at the center. And here is the crucial part. That cloud had been turning, ever so slightly. To begin with, almost everything in the universe has some small amount of spin, and there is an iron rule of physics about spin. When a spinning thing pulls inward, it spins faster. You've seen this with a figure skater. When a skater spins with their arms stretched out wide and then pulls those arms in tight against their body, they whirl faster and faster without pushing off the ice at all. The same motion is simply concentrated into a smaller space, so it has to speed up. This is called the conservation of angular momentum, and the collapsing cloud obeyed it perfectly. As the cloud shrank, its gentle turning sped up into a genuine whirl, and then into a furious rotation. And a furious rotation does something very particular to a cloud of material. It flattens it. Picture a ball of dough spinning in a baker's hands. The faster it spins, the more it flings itself outward at the edges, and the more it flattens into a wide, thin disc, a pizza base spreading out from a spinning lump. That is exactly what happened to the cloud that became our solar system. The center collapsed into a dense, hot ball that would eventually ignite into the sun, and the rest of the material settled into a vast, spinning, flattened disk whirling around that newborn star. We call it the protoplanetary disk, and it is in that flat, turning sheet that the planets were assembled. Tiny grains of dust within the disk bumped into one another and stuck together. Pebbles became boulders. Boulders became mountains. Mountains became worlds. But all of it was built inside the same flat, spinning sheet, because that is where all the material was. So the planets did not scatter in every direction. They could not. They formed within the disk, and they have circled within roughly that same plane ever since. This is why the solar system is flat. This is why the planets line up. The flatness is a fossil, a permanent memory of the spin of that original collapsing cloud, frozen into the architecture of everything that came afterward. And it is not unique to us. When astronomers point their telescopes at other young stars across the galaxy, they see the same thing again and again. They photograph brilliant new stars surrounded by flat, glowing disks of gas and dust, sometimes with dark gaps carved out where infant planets are sweeping up material. Flat disks everywhere. The same process, repeating across the cosmos. There is one fascinating exception, far out at the very fringe of our solar system. Beyond the planets, beyond even the distant belt of icy worlds where Pluto lives, there is thought to be a vast shell of frozen objects called the Oort cloud. And unlike everything else, the Oort cloud is not flat. It is believed to surround the Sun as a great sphere, wrapping our solar system on all sides above, below, and all around at distances so enormous they begin to approach the space between the stars. These are the deep frozen leftovers of our system's birth, flung far outward long ago and stored in the cold dark in every direction at once. And it is from this spherical shell that some comets fall toward us, which is why a few comets arrive not along the plane like the planets, but plunging down from high above or sweeping up from far below. So the solar system is not perfectly flat after all. At its innermost and most active heart, where everything we visit lives, it is a thin disk. But at its faint, frozen outer edge, it puffs out into a sphere. Still, the Oort cloud is so unimaginably distant that it offers us no shortcut. No spacecraft will be threading its way out there to look back at us anytime soon. For everything that matters to our daily lives, the planets, the sun, the wind, the bubble the picture holds, we live in a disk, and the space above and below it stays a frontier. So the disk you should picture around our sun is not an accident. It is the natural shape that matter falls into when it collapses while spinning. And that single fact that everything formed in a spinning sheet is the root of the entire mystery we are exploring tonight. Because the disk is where everything is. The disk is where everything moves. And the disk is the one place where we feel at home, which means the space directly above it and directly below it has stayed nearly untouched, not because there is nothing there, but because nothing has ever had a reason or the means to go there. Now hold that image in your mind, because here is the question almost nobody asks. What is above the disk? What is below it? If our star is sitting in the middle of this enormous flat plate, then there must be a top and a bottom. There must be a region of space directly over the north pole of the sun and another directly under its south pole. Two columns of space, rising and falling away from the plane that everything else lives in. Now, there is something subtle hidden in the word up, and it's worth getting straight before we go further. When we say straight up out of the solar system, we don't mean up the way you mean it standing in your kitchen. In space, there is no universal up or down. There is no floor and no ceiling to the cosmos. The up we are talking about is defined entirely by the disk. It is the direction at a right angle to the plane the planets travel in, perpendicular to that flat sheet, pointing out over the sun's north pole on one side and under its south pole on the other. That is the only thing that makes this up special. It is up relative to us, relative to our flat little neighborhood. And here is a detail that surprises most people. This up, out of the plane of the planets, does not point toward anything grand. It does not aim at the center of our galaxy. It does not line up with the galaxy's own flat disk of stars. In fact, our solar system's plane is tilted at a steep angle compared to the great disk of the Milky Way, leaning over by roughly 60 degrees. So our little spinning plate is tilted inside the much larger spinning plate of the galaxy, like a coin set down crooked on a tabletop. The up out of our solar system is just a local direction, meaningful only to us, pointing out into the general dark. And yet, that humble, local direction, the simple perpendicular to the sheet we were born in, is the hardest direction for us to travel. Not because it leads anywhere special, but because everything we have, every scrap of speed we inherited, is locked into the sheet, and pointing perpendicular to it means fighting all of that at once. And the honest answer is that we have barely looked. We have detailed maps of the surface of Mars. We have close-up photographs of the rings of Saturn, the cracked ice of Europa, the nitrogen glaciers of Pluto. We have images of comets taken from a few miles away. But the regions directly above and below our own star, the closest star to Earth, the one that gives us every sunrise we have ever seen, those regions are still, even now, almost a blank. It seems impossible. How can we have flown to the edge of the solar system and yet never looked down on it from above? The answer comes down to one brutal fact of physics. Going up is expensive. Not a little more expensive. Wildly, almost absurdly more expensive than going outward to the planets. And to understand why, we have to start with a speed that you are carrying right now, this very second, without doing anything at all. You are moving. Right now, as you sit perfectly still, you are racing around our star at a speed that is difficult to even picture. The Earth travels around the Sun at roughly 18.5 miles every second. In the time it takes you to say the word second, our entire planet, oceans, mountains, cities, all 8 billion of us, has slid another 18 miles sideways through space. That's about 67,000 miles per hour. It's worth understanding what that sideways speed is actually doing, because it explains why the Earth doesn't simply fall into the Sun. The Sun's gravity is pulling on our planet constantly, trying to drag it inward. And in a sense, the Earth is falling toward the Sun all the time, never stopping. But because the Earth is also racing sideways so fast, it keeps missing. It falls toward the Sun, and its sideways motion carries it past. It falls again, and misses again, forever. The result of that endless falling and missing is a circle. An orbit. An orbit is not a balance of the planet sitting still in space. It is a perpetual fall that never lands, because the ground keeps curving away beneath it. That sideways speed is the only thing keeping us from plunging into the fire. And that is the deeper irony of the whole problem. The very motion that saves us from falling into the sun is the same motion that traps us in the plane. It is our shield and our prison at once. You feel none of it, because everything around you is moving at exactly the same speed. The air, the ground, your coffee cup, all of it carried along together. But it is happening. It has been happening every moment of your life, and every moment of every life before yours. Now, here is the part that matters. Every rocket we have ever launched starts with that speed already built in. When a probe lifts off from Earth, it isn't beginning from a standstill out in space. It is already moving sideways at 18.5 miles per second, because the planet it left was moving that fast, and it simply inherited the motion. Normally, this is the greatest gift physics ever hands us. If we want to send a spacecraft out to Mars, we do not have to build up that enormous sideways speed from scratch. We already have it. All we have to do is nudge the probe a little, add a small amount of extra speed in the right direction, and that gentle push, riding on top of the speed we already had, carries us across tens of millions of miles to another world. The same is true for Jupiter, for Saturn, for any of the planets. They all share the same flat disk. They are all already moving in roughly the same direction we are. So traveling to them is mostly a matter of fine-tuning a motion we were born with. This is why a trip to Mars, for all its difficulty, is fundamentally a gentle adjustment. A spacecraft bound for Mars doesn't fly in a straight line across the gap. It simply widens its existing loop around the Sun, just enough that the far side of that loop reaches out to where Mars will be. It is coasting, mostly riding the speed it already had, nudged onto a slightly larger circle, and then drifting outward to meet its target. The engine does only a small fraction of the work. The inherited motion does the rest. That is the gift of living in the plane. The whole solar system is already moving together in the same direction at the same tremendous speed, and any trip within that plane gets to borrow all of it. But now, imagine you don't want to go to another planet. Imagine you want to go straight up. You want to leave the disk entirely and climb directly over the North Pole of the Sun. Suddenly, that beautiful inherited speed becomes your enemy, because you are moving 18.5 miles per second sideways, and up is at a right angle to sideways. If you simply fire your engine upward, you don't go up. You go diagonally. The huge sideways motion drags your path back into the disk. To genuinely climb straight up and stay there, you first have to cancel out that sideways speed. You have to bring 18.5 miles per second down to almost nothing. And only then can you start adding the new speed that takes you up and out. This is where the numbers turn frightening. Mission planners have a word for the amount of speed change a spacecraft must produce all on its own, using nothing but its own engine and its own fuel. They call it Delta V. It's the budget of a mission, measured not in dollars, but in speed. Every mission has one. Before a spacecraft is even built, planners add up all the speed changes it will ever need to make the push to leave Earth, the nudges to steer, the burn to arrive, the little corrections along the way, and that grand total is the Delta V budget. It is, in a real sense, the true currency of spaceflight. Not miles, not time. Speed changes. A mission lives or dies on whether its delta V budget fits within the fuel it can carry. And because of the cruel mathematics we just described, a budget that is twice as large does not cost twice as much fuel. It can cost many times more. So when planners look at a destination, the question they really ask is not, how far away is it? It is, how much delta V does it demand? By that measure, the planets are bargains. And the space directly above the Sun is one of the most expensive addresses in the entire solar system. To leave Earth, orbit, and coast out to Mars, you need a delta V of only about 2.5 miles per second. That's the small nudge I described. Affordable. Routine. We do it regularly. But to cancel your sideways motion and climb straight up out of the disk, the delta V you need is roughly 18 miles per second. Almost 10 times as much. And in rocketry, that difference is not 10 times harder. It is vastly more than 10 times harder because of the cruel mathematics of fuel. To carry more fuel, you need a bigger tank. A bigger tank is heavier, so you need even more fuel to push it. That extra fuel needs its own tank, which adds more weight, which demands more fuel still. The requirement spirals. Every extra bit of speed you ask for costs you exponentially more fuel than the last bit did. This isn't a matter of engineering not being good enough yet. It's a wall built into the mathematics of rocketry itself. More than a century ago, a Russian schoolteacher named Konstantin Tsiolkovsky worked out the fundamental equation that governs every rocket ever built or ever to be built. What his equation reveals is harsh and unavoidable. A rocket moves by throwing mass out the back, burning fuel, flinging it out as hot exhaust, and riding the recoil. So the only way to go faster is to throw out more mass, faster. But the fuel you need for the end of the journey has to be carried for the whole journey. It just sits there as dead weight, slowing you down, until the moment you finally burn it. And the fuel needed to carry that fuel has to be carried too. So the relationship between how much speed you want and how much fuel you need is not a straight line. It curves upward, sharply, mercilessly. Want a little speed? Bring a little fuel. Reasonable. Want a lot of speed? The fuel requirement doesn't just grow, it explodes. There is a rough rule of thumb that captures the cruelty of it. Beyond a certain point, every time you want to add another chunk of speed, roughly equal to the speed your exhaust comes out, you have to roughly double the amount of fuel you started with. Add another chunk, double again. And again. And again. This is why a rocket sitting on the launch pad is almost entirely fuel. Look at any large rocket and understand what you are seeing. The tiny capsule at the very top, where the crew or the payload rides, is a sliver of the whole machine. Nearly everything beneath it is tank, and nearly everything in the tank is propellant. The spacecraft is a passenger riding on a skyscraper of fuel that exists for one purpose: to throw itself away as fast as possible. And that whole towering machine is built just to reach orbit, just to climb up off the surface of the Earth and start moving sideways fast enough to fall around the planet instead of back into it. Now, layer the vertical problem on top of that. To go to Mars. Once you are in space, you need that small extra nudge, about 2.5 miles per second of delta V. The rocket equation handles that gracefully. A modest amount of fuel, a modest tank. But to cancel Earth's sideways motion and climb straight up, you need around 18 miles per second of delta V. Feed that number into Tsiolkovsky's equation, and the answer that comes back is almost comical. The fuel required is so enormous, the spacecraft so overwhelmingly dominated by propellant, that no realistic mission could ever be built that way. You would need a fuel tank of such absurd proportions that the tiny instrument you actually wanted to send would be a speck riding an ocean of propellant, an ocean too large to ever launch off the ground in the first place. So a delta V of 18 miles per second is not in a slightly more expensive category than a trip to Mars. It is in another universe of difficulty altogether. This is the prism. The very speed that makes the rest of the solar system easy to reach is the speed that locks us into the plane. We can go around our star with ease. We can hop from planet to planet within the disk. But the moment we try to leave the disk itself to rise above it or drop below it, we have to fight 4.5 billion years of accumulated orbital momentum, all of it at once, with nothing but the fuel we managed to drag up out of Earth's gravity. And so we arrive at one of the strangest, most counterintuitive truths in all of space travel. Reaching Pluto, 3.5 billion miles out across the freezing dark, takes less energy than reaching a point just a few million miles directly above the North Pole of our own star. The far edge of the solar system is easier to touch than the empty space directly over our heads. Let that settle for a moment, because it overturns something we feel instinctively. We tend to assume that nearby means easy and far means hard. The planets are far, so reaching them feels like the great achievement. The space just above the sun is near, so surely it should be simple. But distance is not the thing that costs us. Speed is. Reaching a faraway place in the plane is cheap because we are already moving in the right direction at tremendous speed for free. Reaching a nearby place out of the plane is brutally expensive because getting there means throwing away all of that free speed and starting over. In space, the hardest journeys are not always the longest ones. Sometimes, the hardest journey is the one that asks you to stop moving the way you have always moved. And no journey asks that more completely than the climb straight up out of the only plane we have ever known. So we don't go. Because the climb is so brutally expensive, almost no spacecraft in history has ever made the trip, which means that the two regions directly above and below the sun remain, to this day, one of the last true frontiers in our own backyard. But before we talk about the rare missions that have tried, it's worth asking a deeper question. Why would we even want to go? What is so important about looking down on the sun from above, or up at it from below, that scientists keep dreaming up wild schemes to get there? The answer is that the poles of the sun are where some of the most important and least understood things in the entire solar system actually happen. To see why, we have to spend a moment on what the sun really is. We tend to picture it as a calm, steady ball of light, a reliable lamp in the sky that simply switches on every morning. It is nothing of the kind. The sun is a churning, violent sphere of plasma gas, so hot that its atoms have been torn apart into a soup of charged particles. That plasma is in constant, furious motion, rising and sinking and twisting. To really grasp what is happening up at the poles, it helps to understand the machine underneath. The sun is not solid anywhere. It has no surface you could ever stand on. It is layers of fire wrapped around fire. At the very center sits the core, and the core is where the sun earns its living. There, the pressure is so crushing and the temperature so extreme, around 15 million degrees Celsius, roughly 27 million degrees Fahrenheit, that the nuclei of hydrogen atoms are slammed together hard enough to fuse into helium. This is nuclear fusion, the same process we have struggled for decades to reproduce here on Earth, and the Sun does it effortlessly, constantly, on an unimaginable scale. Every second, deep in that core, the Sun converts millions of tons of matter into pure energy. That energy is born as light, high-energy radiation flooding outward from the core. But it does not escape quickly. Far from it. The energy released in the core takes an astonishingly long time to claw its way to the surface, bouncing and scattering through the dense layers above it for what may be tens of thousands of years before it finally breaks free. The sunlight warming your face today was created in the heart of the Sun long before recorded human history began. Above the core lies a thick zone where energy travels by radiation, creeping outward photon by photon. And above that lies a region where the plasma itself starts to boil. Here, great columns of hot plasma rise toward the surface, release their heat, cool, and sink back down enormous churning cells of fire, like a pot of soup at a rolling boil, but each cell larger than a continent. This boiling layer is the engine room of the Sun's magnetism. Because all that rising, sinking, swirling plasma is electrically charged, and charged material in motion generates magnetic fields. The constant churning twists and stretches and amplifies those fields, winding them up like rubber bands, building the colossal magnetic structure that governs everything dramatic the star does. Above the boiling layer is the part we actually see, the bright, visible surface, where the plasma becomes thin enough for light to finally escape into space. And above the surface, strangest of all, lies the corona. The corona is the Sun's outer atmosphere, a faint crown of plasma that you can normally only glimpse during a total eclipse, when the moon blocks the bright disk and reveals the ghostly halo around it. In fact, for most of history, those rare moments of total eclipse were the only times anyone could study the corona at all. For a few minutes, with the blinding face of the Sun hidden behind the moon, observers could finally see the pale streamers and loops of the outer atmosphere reaching out into space. Those fleeting glimpses revealed that the corona is not a smooth, even glow. It is shaped, structured, sculpted into arcs and rays by the magnetic field beneath it. And the shape of that crown changes with the cycle. When the Sun is calm, the streamers tend to stretch out neatly from the equator. When the Sun is violent, the corona becomes a wild, bristling tangle, reaching in all directions. The magnetic field draws the corona into these shapes, the way iron filings arrange themselves around a magnet and over the poles. In particular, the field opens out into those great streaming plumes that feed the fast solar wind. So even the faint crown we can only glimpse during an eclipse is telling us a story about the magnetic engine below and pointing, once again, toward the poles. And the corona holds one of the great unsolved puzzles in all of physics. It is hotter than the surface beneath it, far hotter. The visible surface sits at around 5,500 degrees Celsius, close to 10,000 degrees Fahrenheit. The corona above it blazes at more than 1,000,000 degrees on either scale. Think about how bizarre that is. As you move away from a fire, you expect things to get cooler, not hotter. Yet the Sun's outer atmosphere is hundreds of times hotter than the surface it sits on top of. Something is dumping enormous energy into the corona, heating it to extremes the surface never reaches, and we still do not fully understand the mechanism. The leading suspects all involve the magnetic field, the same tangled, snapping field that is rooted in that boiling layer and that behaves most simply and most revealingly up at the poles. So, when we talk about wanting to see the poles, this is the context. We are trying to understand a magnetic engine we cannot fully explain, powering an atmosphere we cannot fully explain, on the one star close enough to study in detail. And the clearest window into that engine is the one window we have never been able to look through the view from straight above. And because moving charged particles generate magnetism, the sun is wrapped in a colossal, tangled magnetic field, one that knots and snaps and rearranges itself constantly. This magnetic field is the real engine behind everything dramatic the sun does. It powers sunspots, those dark cooler patches where the field pokes up through the surface. It powers solar flares, sudden brilliant explosions of energy. It powers the coronal mass ejections, vast clouds of plasma flung off into space, the ones that can knock out satellites and light up the sky with auroras when they slam into Earth. And the field is not fixed. It is on a clock. Roughly every 11 years, the entire magnetic field of the sun flips. The north magnetic pole becomes the south, and the south becomes the north. The whole star turns its magnetism inside out, on a schedule, over and over, for as long as it has existed. The most visible sign of all this are the sunspots. A sunspot is a place where the tangled magnetic field has burst up through the surface so strongly that it chokes off the rising heat beneath it. Starved of some of that heat, the spot cools slightly compared to its surroundings, and so it looks dark against the brilliant face of the sun, though it is dark only by comparison, still glowing fiercely in its own right. Some sunspots are larger than the entire Earth. They drift across the face of the sun as it rotates, appear in groups, and fade away over days or weeks. And it is by patiently counting these spots, year after year, that we trace the great cycle. Early in a cycle, the spots appear mostly at the sun's middle latitudes. As the years pass, new spots emerge closer and closer to the equator, while the magnetic action creeps toward the poles. Then, the field flips, the count drops to almost nothing, and the whole pattern begins again, reversed. It is a vast, slow, magnetic breathing in and out, north and south, playing out across the entire star, decade after decade. We have known about this 11-year cycle for a long time. We can watch the sunspots come and go. But the deep machinery behind it, the actual process that builds the field up, tears it down, and rebuilds it backwards, is something we still do not fully understand. There are competing ideas about exactly how the sun generates and reverses its magnetism, what scientists call the solar dynamo. Some models say the crucial action happens deep down, near the base of that boiling layer, far below the surface. Others argue that much of it plays out closer to the top, in the shallower layers we can almost see. These theories make different predictions about how the magnetic field should behave near the poles, how it should be arranged there, how it should drift and flip as the cycle turns. A clear, sustained view from directly above the pole could tell these competing pictures apart. It could show us which model of the sun is closer to the truth. And that is not only about the sun. Every star runs on some version of this same magnetic machinery. Learn how the dynamo works on our star, the one we can actually examine up close, and we learn something about the inner workings of stars across the entire universe. So the stakes of that polar view stretch far beyond a single mission and a single star. And the best evidence we have suggests that this whole process begins and is governed at the poles. The poles are where the magnetic field is at its simplest and most exposed. They are where the great reversal seems to start. And there is a powerful, practical reason this matters. The strength of the Sun's magnetic field at its poles during the quiet years of the cycle appears to be one of the best forecasters we have of how strong the next cycle will be. A strong polar field now tends to foretell a vigorous, stormy cycle to come. A weak one hints at a gentle cycle ahead. So the poles are not just where the engine resets. They may hold an early warning of the Sun's future temperament, a clue to how violent the coming years of space weather will be. And yet, we measure that crucial polar field today almost entirely from the side, at a steep, awkward angle, squinting at the very edge of the Sun's disk, where our view is worst. It is precisely the region we most need to see clearly, observed from precisely the worst possible vantage. If you want to understand the heartbeat of the Sun, the poles are where you would place your hand to feel the pulse. This rhythm is not a recent discovery, and it is not a harmless curiosity. It reaches all the way down to Earth. Humans have been counting sunspots for centuries, ever since the first telescopes were turned toward the Sun in the early 1600s. Over time, observers noticed a pattern hidden in the count. The sunspots wax and wane. In some years, the Sun's face is freckled with dozens of dark spots. A few years later, it can be almost clean. Then, the spots return. That rise and fall, peak to peak, traces out the 11-year cycle, the visible expression of the great magnetic engine winding up and reversing. At the peak of the cycle, called solar maximum, the Sun is at its most active and violent, bristling with spots, hurling out flares and great clouds of plasma. At the low point, solar minimum, it grows calm and quiet. And the strength of that cycle has not always been the same. In the late 1600s, for a stretch of about 70 years, the sunspots nearly vanished altogether. Observers of that era looked, and for decades found almost nothing. The Sun fell unusually quiet. That long lull is called the Maunder minimum, and it overlapped with a period of bitterly cold winters across parts of the world, a connection scientists still study and debate. It is a reminder that the activity of the Sun is not a fixed, eternal hum. It shifts. It has moods that last for generations. And those moods can reach across 93 million miles of empty space and touch our weather, our climate, our lives. The more violent side of the cycle reaches us too, and far more dramatically. When the Sun unleashes a major flare or flings out a coronal mass ejection aimed at Earth, that wave of charged particles slams into our planet's magnetic field. Most of the time, the result is beautiful and harmless. The shimmering curtains of the auroras, the northern and southern lights, glowing green and red over the polar skies. But a powerful enough storm can do real damage. In 1859, the most intense solar storm in recorded history struck the Earth. It is known as the Carrington event, named for the astronomer who watched the flare erupt. The telegraph network, the cutting-edge technology of that age, went haywire. Wires sparked. Some operators received shocks. Some lines kept working, even after their power was disconnected, running on the electrical currents the storm itself had induced. Auroras blazed so far from the poles that they were seen near the tropics, and people in some places woke in the middle of the night, thinking dawn had arrived. A storm of that scale striking our modern world would be a far more serious matter. Our entire civilization is now wrapped in delicate technology. Power grids spanning continents, satellites threaded through the sky, communication and navigation networks we lean on every hour of every day. A direct hit from a Carrington-class storm could knock out power across whole regions, disable satellites, and disrupt the systems that modern life quietly depends on. This is the field of space weather, and it is not science fiction. Agencies around the world monitor the sun constantly, watching for the storms it sends our way. And every one of those storms is born from the magnetic engine we have been describing, the same engine whose deepest workings begin at the poles. So studying the poles is not an academic indulgence. It is part of learning to forecast the violence of the star we depend on before it reaches us. There's more. The sun is constantly blowing. A steady stream of charged particles pours off its surface in every direction, flooding outward through the entire solar system. This is the solar wind, and it never stops. But it is not the same everywhere. Near the sun's equator, the band that lines up with the disk where the planets live, the solar wind is slow and gusty and turbulent. It moves at around 250 miles per second, churning and uneven. And here is a small mystery tucked inside that. We have a reasonably good idea of where the fast wind comes from. It pours out of those open magnetic chimneys, the coronal holes, which sit most reliably over the poles. But the slow wind, the gusty stuff near the equator, is harder to pin down. Exactly where on the sun it originates and how it is released is still debated. It seems to leak out from the edges of magnetic structures and tangled regions near the sun's middle, but the details remain unsettled. It is a strange situation. The wind that constantly washes over our own planet, the slow wind, here in the plain is the wind whose birthplace we understand least. A better view from outside the plane, watching both winds emerge from their sources at once, could finally untangle where each one truly begins. But over the poles, something different happens. In those polar regions, there are features called coronal holes, places where the magnetic field, instead of looping back down into the sun, opens straight out into space like a chimney. And through those open chimneys, the solar wind pours out far faster and far smoother. Over the poles, the fast solar wind streams outward at somewhere between 400 and 500 miles per second, roughly twice the speed of the slow wind near the equator. There is one more feature of all this that captures just how three-dimensional the sun's influence really is. The sun's magnetic field, carried outward by the solar wind, does not fill space evenly. It folds into a vast, rippling surface that wraps around the whole solar system. Because the sun's magnetic poles are slightly tilted compared to the axis it spins on, and because the sun rotates, this surface gets dragged into enormous waves. Scientists describe the result as a ballerina skirt, a great undulating sheet that flares out from the sun's middle and ripples up and down as it spreads outward through the planets. We live near the folds of that skirt, crossing from one side of it to the other as the sun turns and the waves wash past us. It is a structure that only truly makes sense in 3 dimensions, seen from outside the plane. From down inside it, edge on, we can only ever catch glimpses of its shape. This fast polar wind shapes the space weather of the entire solar system. It helps determine how the sun's influence pushes out against the galaxy beyond. It affects every planet, every spacecraft, every astronaut. And here is the staggering part. For almost all of human history, we have studied this wind, and these magnetic reversals, and this whole violent star almost entirely from the side, from the plane of the disk, from the equator's point of view. Imagine trying to understand the weather of an entire planet while being allowed to stand only at the equator, never once permitted to look down on the poles from above. You would learn a great deal, but you would be missing the part of the story where so much of the action begins. That is exactly the position we have been in with our own star. We have a magnificent side view. We have almost no view from the top or the bottom. There is a fitting parallel in the history of exploring our own planet. When humans set out to map the Earth, the poles were the last places we reached. The coastlines, the continents, the tropics, the temperate lands, all of those were charted long before anyone stood at the top or the bottom of the world. The north and south poles of the Earth were the final blanks on the map, the hardest places to reach, claimed only after the rest of the planet was already known. There is something almost poetic in the fact that the same is true of our star. We have mapped the sun's middle in extraordinary detail. We have watched its equator for centuries. And its poles, just like the Earth's, are the last frontier, the final regions to be seen, the hardest corners of the most familiar object in our sky. The poles always seem to come last, on our world and on our star alike. So how rare is it, really, to get above the sun? In the entire history of space exploration, you can count the missions that have managed a true polar view of the sun on the fingers of one hand, with fingers to spare. For decades, there was essentially one. The mission was called Ulysses. It launched in 1990, a joint effort between NASA and the European Space Agency. And the way Ulysses solved the impossible problem of climbing out of the disk is so clever and so strange that it tells you everything about how hard this really is. The team behind Ulysses knew they could never carry enough fuel to cancel Earth's sideways motion directly. No rocket of that era could. So they cheated, using gravity. Instead of aiming up, they aimed outward all the way out to Jupiter. The spacecraft flew across the solar system to the largest planet we have, and as it passed, it dove through Jupiter's enormous gravitational field. Jupiter is so massive that its gravity can fling a passing spacecraft onto a completely new path, like a sling whipping a stone. Ulysses used that giant slingshot not to speed up and fly farther out, but to bend its trajectory nearly straight up, tilting its orbit almost 80 degrees out of the flat plane of the planets. In other words, the only practical way we found to climb above the sun was to first fly hundreds of millions of miles in the wrong direction, all the way to Jupiter, and borrow the gravity of a giant to throw us up and out. It worked. Ulysses fell back inward on its new tilted path and, for the first time in history, flew over the poles of the sun. It gave us our first direct measurements of that fast polar wind streaming out of the coronal holes. It mapped the magnetic field from angles no one had ever sampled. It was a triumph, and it kept going for far longer than anyone expected. Ulysses was originally meant for a relatively short mission, but it endured for more than 18 years, looping up over one pole of the sun and down under the other, again and again, across 2 complete solar cycles. It flew over the poles during the sun's quiet years and came back to fly over them again during the violent years, letting scientists see how the polar wind changed as the great cycle turned. and it returned genuine surprises. It confirmed that the fast solar wind really does pour steadily out of the open coronal holes at the poles, while the slow, gusty wind belongs to the busy middle latitudes, a clean division of the sun's exhalation into two distinct streams. It found that cosmic rays from deep space were leaking into the inner solar system in ways the old models had not predicted. It discovered that the sun's magnetic influence, stretching out into space, was more uniform, more evenly spread from equator to pole than anyone had assumed. And on its long looping path, it even flew, by chance, through the tail of a comet, sampling material no one had planned to taste. Every one of those findings came from simply being somewhere no spacecraft had ever been above and below the plane, looking at the sun from a fresh angle. It was proof of how much we had been missing by only ever watching from the side. But there was one heartbreaking limitation. Ulysses was built with the instruments of its time. It carried detectors to taste the particles and feel the magnetic fields it flew through. It did not carry a camera capable of photographing the poles. So Ulysses could tell us what the conditions were like up there. It could measure the wind and the field and the particles. But it never sent home a single picture of what the top or bottom of the sun actually looks like. We learned about the poles. We never saw them. For nearly 30 years, that was where things stood. Think about that gap. 3 decades passed between the first mission to fly over the sun's poles and the next one to truly tackle the problem. In those same 30 years, we sent orbiters and landers and rovers to Mars again and again. We flew past every outer planet. We visited comets and asteroids. We photographed Pluto up close. The whole rest of the solar system was being explored and re-explored, while the poles of our own star sat almost entirely neglected, not because no one cared, but because the climb was simply so hard and so costly that it kept losing out to easier, cheaper destinations within the plane. The vertical direction was the road no one took, decade after decade, precisely because physics had made it the steepest road of all. And then, very recently, the second great polar mission arrived. Its name is Solar Orbiter, and it is a European Space Agency spacecraft launched in 2020. Solar Orbiter took a different, more patient route than Ulysses. Instead of one dramatic slingshot around distant Jupiter, it has been making repeated close passes by Venus. Each time it swings by that planet, Venus's gravity gives its orbit a small tilt, nudging it a little further up out of the disk. Pass after pass, year after year, that orbit is slowly being lifted, like someone walking a heavy ladder up against a wall, one careful step at a time. To survive the journey, Solar Orbiter had to be built tough. It travels close enough to the sun that it must hide behind a specially designed heat shield, a dark barrier coated in a material partly made from burnt animal bone, which can endure temperatures of up to around 500 degrees Celsius, over 900 degrees Fahrenheit, while keeping the instruments behind it cool. The spacecraft peers at the sun through small windows in that shield, opening and closing them like cautious eyes. And it carries a whole suite of instruments, some that photograph the sun directly, others that measure the wind and the magnetic field flowing past the spacecraft itself. The goal is to link the two, to watch a patch of activity erupt on the sun's surface, and then, a little later, feel the wind from that very patch wash over the spacecraft, to connect cause and effect across millions of miles. Even before it began tilting toward the poles, Solar Orbiter was making discoveries. On its early close approaches, its cameras revealed something no one had clearly seen before. Countless tiny flickers of activity dancing across the sun's surface, miniature bursts that scientists nicknamed campfires. These little flares are minute by the sun's standards, but there are vast numbers of them, everywhere, all the time. And they may be part of the answer to that great unsolved puzzle of why the corona is so impossibly hot. Countless small fires, together, helping to heat the sun's outer atmosphere. And Solar Orbiter carries something Ulysses never had: cameras. In March of 2025, after years of patient tilting, Solar Orbiter climbed high enough above the plane to point its cameras down toward the bottom of the sun. And it sent home the first images of the sun's south pole ever captured in human history. Think about how astonishing that sentence is. The sun has been shining over our world for 4.5 billion years. Humans have worshipped it, tracked it, built monuments aligned to it, studied it with telescopes for centuries. And yet, it was only in 2025, within the last year, as of this video, that any human or machine ever managed to look at the bottom of it and take a picture. Sit with that for a moment. For all of human history, every culture that ever lived watched the sun rise and set. They built temples aligned to it, told stories about it, ordered their entire calendars around it. They could see its bright face. They could feel its warmth. On rare days, during an eclipse, they could even glimpse the ghostly halo of its corona. But the top of it, and the bottom of it, stayed pure imagination, a thing no one could ever observe, no matter how powerful the telescope, because from down here, in the plane, we only ever see the sun's middle, turned edge-on to us. Until 2025, the poles of our own star were as unseen as the far side of the moon was before the first spacecraft flew around it. A blank spot on the most familiar object in our sky. And now, at last, that blank is beginning to be filled. The images revealed a region that looks nothing like the smooth, familiar face of the sun we see from Earth. The South Pole appeared as a chaotic, magnetically scrambled place, with patches of north and south magnetic polarity jumbled together in a way that does not happen anywhere else on the star. It was a glimpse of the messy machinery that drives that 11-year cycle, a first blurry look at the gears of the engine. And the timing of those first images was telling. They were captured at a moment when the sun's magnetic field was in the middle of one of its great reversals, the old field breaking down, the new one not yet settled. That is exactly why the South Pole looks so jumbled, with patches of opposite magnetic polarity crowded together where, in calmer times, a single clean polarity would reign. We were, in effect, catching the sun in the act of turning itself inside out, seeing the chaos of the changeover at the very place where that changeover begins. It was a first, tantalizing taste of the kind of science a true polar mission could deliver, if only we could get a steadier, closer, longer look from directly overhead. And it is only the beginning. Solar Orbiter is meant to keep tilting, climbing towards steeper and steeper viewing angles in the years ahead, sending back better and better views of both poles. In its first years, it was looking at the sun more or less from the side, like all the spacecraft before it. But with each new swing past Venus, its orbit is being tipped further over, and in the years to come, it is expected to reach viewing angles steep enough to look down on the polar regions far more directly than ever before. When it does, scientists hope to watch something they have never been able to follow, clearly, the slow march of magnetism across the face of the Sun as the cycle turns. Over the years of a cycle, magnetic field drifts from the Sun's middle latitudes up toward the poles, helping to cancel the old field and build the new, reversed one. That migration is one of the central clues to how the whole 11-year rhythm works. And we have never been able to watch it happen cleanly at the poles because we have never had a steady view from above. Solar Orbiter, climbing higher with every pass, may finally give us that view. Not a single snapshot, but a sustained look at the Sun's magnetic engine resetting itself, observed from the one angle that reveals it best. Now, you might wonder about another famous mission you may have heard of. There is a spacecraft called the Parker Solar Probe that has flown closer to the Sun than anything ever built. It has dived through the Sun's outer atmosphere, enduring temperatures and radiation that would destroy almost anything. It is one of the boldest missions ever flown. It used repeated swings past Venus to draw its loop tighter and tighter around the Sun, until it was passing through the corona itself, the outer atmosphere we can normally only see during an eclipse. At its closest approaches, it became the fastest object humans have ever built, whipped to staggering speeds by the Sun's gravity as it skimmed the edge of the fire and raced back out again. It is, in many ways, the closest cousin to the kind of dive and obert maneuver would require proof that we can build a craft tough enough and fast enough to survive a brush with the Sun. But notice something. Parker dives in close, and it loops around the Sun's middle. It studies the Sun by getting near it, not by getting above it. It stays, more or less, in the plane. That tells you something important. We have built a probe daring enough to touch the Sun's atmosphere. And it is still easier to do that to plunge into the fire near the equator than it is to climb high above the pole and look down. And consider this. Of all the hundreds of billions of stars in our galaxy, there is exactly one whose poles we could ever realistically hope to photograph. Every other star in the sky is so far away that, even through our finest telescopes, it remains nothing but a single point of light, a pinprick, with no surface, no poles, no detail at all that we can resolve. We will likely never see the pole of another star, not for centuries, perhaps not ever. Our Sun is the single exception. The one star close enough to study as a place rather than a point. The one whose top and bottom are even theoretically within reach. And we have only just, in the last year, managed to glimpse one of them for the very first time. That makes the missing view not just a gap in our maps of the solar system. It makes it a gap in our understanding of stars themselves, because the only stellar pole we will ever get a proper look at belongs to our own. There is a second reason that climbing above the disk matters so much. And this one is even stranger, because it concerns something we live inside but have never actually seen. Our home in the galaxy is not just the planets. The Sun's influence reaches out far beyond the most distant world. That endless solar wind we talked about, the river of charged particles pouring off the star in every direction, does not blow forever. It carves out a vast bubble in space. Inside that bubble, the Sun rules. Its wind and its magnetic field fill the space between the planets and push outward against everything beyond. This bubble is called the heliosphere. And it is enormous, reaching far past Pluto, far past the most distant comets we have catalogued, out to a boundary tens of times farther from the Sun than Earth is. To get a sense of that scale, remember how far the Voyager probes have traveled. They have been flying outward for nearly half a century, among the fastest objects we have ever launched. And they only crossed the edge of the bubble in the last decade or so. That is how vast the heliosphere is. Our fastest emissaries needed lifetimes to reach its outer wall. Everything that has ever happened in human history has happened deep inside this single bubble, this one shell of the sun's making, drifting quietly through the galaxy. That boundary is not a sharp wall. It is a series of layers, a frontier with structure to it. As the solar wind streams outward, it eventually races into the thin gas of interstellar space, pushing back the other way. At some point, far beyond the planets, the solar wind slams into that resistance and abruptly slows, going from a fast outward gallop to a churning crawl. That sudden slowdown is called the termination shock, a vast, invisible shockwave wrapped around the entire solar system, where the wind from our star first feels the pressure of the galaxy. Beyond the termination shock lies a turbulent, sluggish region where the slowed solar wind piles up and swirls, mixing with the inflow from outside. This is the heliosheath, the outer skin of our bubble, thick and choppy and strange. And at the very outer edge of the heliosheath lies the true frontier, the heliopause. The heliopause is the line where the sun finally loses. It is where the pressure of the solar wind, pushing out, exactly balances the pressure of interstellar space, pushing in. Cross it, and you have left the sun's bubble entirely. You are in the space between the stars. And just outside that boundary, there was long thought to be one more feature. Because the solar system moves through the galaxy, scientists expected our bubble to push up a bow wave ahead of it, the way a boat shoves up a wave of water at its front as it moves forward. For years, the textbooks showed a sharp shock standing out in front of the heliosphere, where it slammed into the oncoming interstellar gas. But more recent measurements suggested the solar system may be moving through the surrounding gas more gently than once believed. Gently enough, perhaps, that there is no sharp shock at all, only a softer, milder swell pushed ahead of us, rather than a crashing wall. It is yet another feature of our own neighborhood, whose very existence we have had to revise, simply because we cannot get far enough out or far enough above to see it plainly. That is the boundary the Voyager probes eventually punched through the outermost shell of our home. And even those two crossings held surprises. As each Voyager approached the edge, scientists watched the readings change in ways the models had not quite predicted. The count of cosmic rays from deep space climbed sharply as the spacecraft pushed outward, while the particles from our own sun fell away, the clearest sign that the craft was leaving the sun's domain and entering the galaxies. The boundary itself turned out to be more layered and more textured than expected, with the spacecraft lingering in strange transitional zones before finally breaking through. These were just two narrow keyholes punched through the wall of an enormous structure, and even they overturned expectations. It is a reminder that whenever we finally reach a place we have never been, the universe almost always turns out to be stranger than our models said it would be. Which is exactly what makes the unseen view from above so tantalizing. Inside the heliosphere is everything we think of as home, every planet, every moon, every comet, every spacecraft we have ever launched. You, me, our whole world. Outside it lies interstellar space, the true space between the stars, filled with the thin gas and dust of the galaxy, and laced with cosmic rays. And our little bubble does not sit still in that gas. It is moving through it. The entire solar system is sweeping through the galaxy at a brisk pace. And right now, it happens to be passing through a wisp of gas that astronomers call the local interstellar cloud, a thin, warm patch of material drifting in our neighborhood. That cloud, in turn, sits inside a much larger and emptier region called the local bubble, a vast cavity in the galaxy carved out long ago by ancient exploding stars, swept nearly clean of dense gas. So our home is a bubble, inside a cloud, inside a bubble, shells within shells. And as the solar system plows forward through the surrounding gas, it is the heliosphere that meets that gas first, the leading edge of our bubble taking the pressure, shaping the flow, deciding how much of the galaxy gets in and how much is held at bay. Cosmic rays are particles flung across the galaxy by distant exploding stars and other violent events, traveling at nearly the speed of light. And the heliosphere acts like a shield against a large fraction of them. The sun's bubble deflects much of that galactic radiation, keeping the inside of the solar system and our planet partly protected. So this bubble is not some abstract curiosity. It is the shell we live inside. It is part of what keeps the harshest radiation of the galaxy at arm's length. And here is the embarrassing truth. We do not actually know what it looks like. We cannot tell you, with confidence, the shape of our own home in the galaxy. For most of the modern space age, the textbook picture was simple and intuitive. The solar system is moving through the galaxy. As it moves, it plows through the thin gas of interstellar space. So scientists pictured the heliosphere like the bubble around a moving boat, or like a comet. A rounded nose at the front, where the bubble pushes against the oncoming galactic wind, and a long tail streaming out behind, trailing away in the direction we came from. For decades, that comet shape was simply what everyone drew. It was a reasonable guess. It matched the data we had. But in 2020, a team of researchers led by the scientist Merav Ofer at Boston University built a new and more sophisticated computer model using fresh data from NASA spacecraft. And the model came back with a very different shape. According to their work, the heliosphere may not have a long comet tail at all. Instead, it may look more like a deflated croissant, a curved central bulge with two short, blunt jets curling away from it and no long trailing tail behind. A crumpled crescent drifting through the galaxy. The reason the shape is so hard to pin down comes back to a deceptively simple problem. The heliosphere is not a solid object with a clean edge. It is a fuzzy, shifting balance between two pressures, the solar wind pushing out and the interstellar gas pushing in. That balance depends on things we only partly know. Exactly how strong the wind is in every direction, exactly how dense the gas is outside, exactly how the magnetic fields on both sides are arranged. Feed slightly different assumptions into the models, and they hand back dramatically different shapes, some long-tailed, some blunt and rounded, some crumpled into that strange crescent. The models are only as good as the measurements we feed them. And our measurements are taken almost entirely from one spot inside the bubble, looking out. It is a bit like trying to work out the exact shape of a balloon while sitting inside it in the dark, able only to press a hand against the wall here and there. You can make excellent, educated guesses. You cannot simply look and know. And so the true shape of our home in the galaxy remains, remarkably, an open question. Now, not every scientist agrees with this. The shape of the heliosphere is genuinely contested, and other models still favor something more elongated. But that disagreement is exactly the point. We are arguing about the shape of the place we live, and we cannot settle it. Why can't we? Because we have never seen it from outside. The only direct measurements we have of the edge of the bubble come from two spacecraft. The two Voyager probes, launched back in 1977, have been flying outward for nearly half a century. Voyager 1 crossed the boundary of the heliosphere, a region called the heliopause, where the sun's wind finally gives way to interstellar space in 2012. Voyager 2 crossed it in 2018. Those crossings were historic. For the first time, human-made objects had passed beyond the sun's bubble into the space between the stars. It is worth pausing on what those two spacecraft have done. They were launched in the 1970s, built with technology more primitive than the phone in your pocket, and they are still flying, still working, still whispering faint signals back to Earth across a gulf so vast that their messages now take many hours to reach us, traveling at the speed of light the entire way. They are the most distant objects humanity has ever made, billions upon billions of miles away, so far that the sun has shrunk to little more than a very bright star in their skies. Their power is slowly fading, drawn from the steady decay of a small nuclear source on board, and one by one their instruments are being switched off to conserve the last of it. In time, perhaps within years, they will fall silent for good and drift onward forever, no longer able to call home. But for now, they remain our only two direct emissaries, beyond the bubble, our only first-hand reports from the far frontier. And that is exactly why their limitation matters so much. But notice the limitation. Both Voyagers left more or less sideways. They departed along the disk, roughly in the plane of the planets. They each punched through the wall of the bubble at a single point, in roughly the same general region. It's like trying to learn the shape of an entire house by stepping outside through two windows that are right next to each other and feeling the wall on your way out. You learn something real about that one patch of wall. You learn almost nothing about the roof, or the far side, or the overall shape of the building. To truly understand the form of our bubble, you would want to rise high above it. You would want a probe to climb up out of the plane, far enough and high enough to look back down and see the whole structure laid out beneath it. A vantage point above the disk, gazing down at the shape of our home in the galaxy. We have tried to map the bubble in a clever, indirect way from the inside. There was a small NASA spacecraft called IBEX, the Interstellar Boundary Explorer, that did something ingenious. It could not travel to the distant edge of the heliosphere. So, instead, it sat near Earth and detected particles arriving from that edge. At the boundary, far out where the solar wind meets the galaxy, some particles get electrically neutralized and come flying back inward across the whole solar system, carrying information about the conditions out at the frontier. IBEX caught those returning particles, one by one, and used them to build a map of the boundary, not by going there, but by reading the messages it sent back. And that map held a complete surprise. Stretching across the sky, IBEX found a bright, narrow band of these particles, a long arc that nobody had predicted and nobody fully understands. Scientists simply call it the ribbon. It appears to be tied somehow to the direction of the magnetic field in the space just outside our bubble, draping around us like a seam. But its exact cause is still argued over today. It is a startling thing to realize. We discovered a giant structure wrapped around the edge of our own solar system, and we are still not certain why it is there, precisely because we cannot get far enough away to look at the boundary directly, and see for ourselves. There is a newer NASA mission, launched in 2025, called IMAP, the Interstellar Mapping and Acceleration Probe. It is designed to study the boundary of the heliosphere in far greater detail by detecting particles that come streaming back in from the edge. It will sharpen our picture enormously, working cleverly from the inside. Stationed at a stable point between the Earth and the Sun, IMAP catches those particles drifting back in from the distant boundary, gathering them in far greater numbers and far finer detail than anything before it. From that steady perch, it can build sharper maps of the edge of our bubble, study how particles are flung to enormous energies out there, and keep watch on the stream of interstellar material trickling into the solar system from the galaxy beyond. It is a remarkable piece of work, squeezing knowledge of a boundary tens of billions of miles away out of faint signals collected close to home. But even IMAP looks outward from within the bubble. For a true, direct view of the bubble's real shape, for an actual look down at the structure from above, there is still only one way. Climb out of the plane, rise above the disk, and look back. And we have already seen how staggeringly hard that climb is. So we are left in a remarkable position. We live inside a structure tens of billions of miles across. It shields us from the radiation of the galaxy. And we have never once seen its true shape, because the only place to see it from is the one direction physics makes hardest to reach up and out, above the plane. And the shape is not a trivial detail. The size and form of the heliosphere determine how well it shields the inner solar system from cosmic rays. A larger, more robust bubble holds more of that galactic radiation at bay. A smaller, weaker one lets more of it through, deeper toward the planets. Now remember that the solar system is drifting through the galaxy, and the gas around it is not always the same. Right now, we travel through a relatively thin patch, but over millions of years, the sun's path will carry it into denser clouds of interstellar gas. When that happens, the pressure from outside rises, and the bubble can be squeezed smaller, pressed inward, perhaps even shrinking past the outer planets. A more compressed bubble means a weaker shield, and more cosmic radiation reaching the inner solar system over long stretches of time. Some scientists have wondered whether such passages through denser gas far back in Earth's history could have left their mark on our planet's climate, or even on the long story of life here. It is a question we cannot fully answer, in part because we do not yet know the true shape and strength of the bubble even today. Understanding that shape, really understanding it, from outside is a step toward understanding how our home has weathered its long journey through the galaxy, and how it will weather what lies ahead. So, how do you actually solve this? If you can't carry enough fuel to cancel 18.5 miles per second of sideways motion, and you can't always borrow a giant planet's gravity, what's left? This is where the story turns genuinely beautiful, because the solution is so deeply counterintuitive that it feels almost like a riddle. To climb away from the sun, you first have to fall toward it. The trick is called the solar Oberth maneuver, and it works backwards from everything your instincts tell you. It is named after Hermann Oberth, one of the founding theorists of rocketry, who worked out the underlying principle back in 1929. Here is the idea. Normally, if you wanted to escape, you would point your engine away from the sun and try to climb, fighting gravity the whole way. The Oberth maneuver says, don't do that. Do the opposite. Take your spacecraft and let it fall. Let it drop inward toward the sun with its engine off. As it falls, the The sun's gravity pulls on it harder and harder, and the spacecraft picks up tremendous speed. By the time it reaches its closest approach, the point called perihelion, skimming low over the sun, it is moving astonishingly fast. Falling that deep into the sun's gravity, a spacecraft can be racing along at more than 60 miles per second. Of course, getting that close to the sun is its own ordeal. Down at the bottom of such a dive, the spacecraft is bathing in heat and radiation of staggering intensity, the kind of environment that would simply melt an unprotected machine. This is the same brutal challenge that the Parker solar probe was built to survive. Hiding behind a thick shield that takes the full fury of the sun, while the delicate instruments shelter in its shadow, kept relatively cool, just inches behind a face, glowing at well over 1,000 degrees Celsius, more than 2,500 degrees Fahrenheit. Any spacecraft attempting an Oberth dive would need that same kind of armor, a heat shield, able to endure the inferno for the crucial minutes of the burn. So this maneuver asks a great deal. It demands a craft tough enough to survive the plunge, precise enough to fire its engine at exactly the right instant, and clever enough to come out aimed in just the right direction. But the prize is enormous. Because, if it works, the very gravity that makes the climb impossible by ordinary means becomes the thing that powers the escape. And then, at that exact moment of closest approach, at maximum speed, you fire your engine. Why does this matter? Why fire the engine then, instead of later? Because of the principle Oberth worked out nearly a century ago. A rocket engine produces dramatically more useful energy when it fires, while the spacecraft is already moving fast and sitting deep in a gravity well. The same amount of fuel, burned at high speed close to the sun, adds far more energy to your orbit than that same fuel would add if you burned it slowly out in empty space. The deep dive turns your engine into something far more powerful than it would otherwise be. You are essentially using the sun's own gravity to supercharge your fuel. By burning at the bottom of that fall, at maximum velocity, you wring far more out of every drop of propellant than you could anywhere else in the solar system. There is a way to feel why this works, even without the mathematics. When you fire your engine, the fuel you burn carries a fixed amount of chemical energy locked inside it. But how much of that energy ends up as useful motion of your spacecraft rather than wasted in the leftover speed of the exhaust depends on how fast you are already going. If you are already moving extremely fast, the exhaust you throw out behind you ends up nearly motionless once it leaves, which means almost all of the fuel's energy went into the spacecraft and almost none was wasted. The faster you are already traveling when you burn, the more of the fuel's energy you keep. And nowhere in the solar system can a spacecraft travel faster than at the bottom of a deep plunge toward the sun. So the sun's own gravity does the spacecraft a double favor. First, it accelerates the craft to tremendous speed for free, simply by pulling it inward. Then, because the craft is now moving so fast, every drop of its own fuel becomes far more potent at the very moment it is burned. This is the same family of trick that Ulysses used at Jupiter, and that Solar Orbiter uses at Venus, letting gravity do work that fuel alone never could. A spacecraft swinging close past a planet can steal a little of that planet's motion, getting flung onward faster than it arrived, without spending a drop of propellant. We have used these gravity assists for decades to reach the outer planets, slinging probes from world to world like a stone skipped across a pond. The solar Oberth maneuver takes that same philosophy and aims it at the sun itself, the largest gravity well in the entire solar system, and uses it not to fly farther out, but to gain the speed needed to break free of the plane and climb. After that burn, the spacecraft is screaming along on a brand new path, fast enough and aimed well enough that it can finally tear itself up out of the plane and climb toward the poles, or even out of the solar system entirely. The fall becomes the launch pad. You drop toward the fire in order to be flung up over the top of it. Picture how such a journey might unfold from start to finish. A spacecraft leaves Earth and, instead of climbing, lets itself drift inward, falling toward the sun along a long, looping path. For months it falls, the sun growing larger and fiercer ahead of it, its heat shield turned to face the rising glare. Then comes the closest approach. The craft skims low over the blazing surface, racing at tremendous speed, the shield taking the full fury of the star. And in that brief, critical window, just minutes long, the engine fires. The burn is short, but because the craft is moving so fast and sitting so deep in the sun's gravity, it does the work of a far larger burn made anywhere else. When the engine cuts off, the spacecraft is on a wholly new path, flung up and out of the plane, rising away from the disk that every planet shares, climbing toward the pole. From there, perhaps with a sail spread wide to the sunlight, it continues its slow ascent into the empty heights above the star. And finally, weeks or months later, it reaches the place no machine has ever been high above the pole of the sun, and turns its instruments around to look back down. That is the shape of the mission. A fall, a burn, a climb, and at last, a view. It is one of the most elegant ideas in all of spaceflight, and after decades of living mostly in textbooks and academic papers, it is now being seriously studied for real missions. There is a second approach too, and it could not be more different in character. Where the Oberth maneuver is violent and dramatic, a screaming dive and a sudden burn, this one is patient and almost gentle. Solar sails. A solar sail is exactly what it sounds like. An enormous, gossamer-thin sheet of reflective material spread out across thousands of square meters. So thin, it is measured in fractions of the width of a human hair. And it uses no fuel at all. Instead, it catches sunlight. Light is made of particles called photons, and although a single photon is unimaginably tiny, photons carry a tiny push. When sunlight strikes a mirror, it gives that mirror a faint nudge. For everyday objects, the nudge is far too small to notice. But spread out a vast feather-light sail in the constant glare of the sun, and that endless pressure of light builds, second after second, day after day, year after year. A solar sail doesn't accelerate hard. It accelerates forever. As long as the sunlight keeps falling on it, the push never stops. And by tilting the sail, you can steer that push. You can use it to gradually, patiently lift a spacecraft's orbit out of the plane, tilting it a little more with every loop around the sun. It can take years. A sail spirals upward slowly, almost imperceptibly, but it needs no propellant whatsoever. It simply rides the light. And the longer it pushes, the steeper the climb it can eventually reach. And this is not merely a theory waiting on a chalkboard. Solar sails have already flown. In 2010, a Japanese spacecraft named Ikaros unfurled a sail in deep space and became the first craft in history to be measurably driven by the pressure of sunlight alone, sailing through the inner solar system on light. A few years later, a privately funded mission called LightSail spread its own shining sheet in orbit around the Earth and demonstrated that it, too, could change its path using nothing but photons. These were small, modest craft. But they proved the principle in the most direct way possible by actually doing it. Sunlight can push a spacecraft. We have watched it happen. The challenge now is one of scale and patience building, sails large enough, light enough, and durable enough to spend years spiraling inward and tilting upward, riding that gentle, endless push all the way out of the plane. Mission concepts that would use exactly this technique have been proposed for years, with names like the Solar Polar Imager and various high-inclination solar missions spacecraft designed to ride sunlight up and over the poles of the sun. And here is the most exciting possibility of all. You don't have to choose. Imagine a spacecraft that combines both ideas. It uses a solar sail to slowly spiral closer and closer to the sun, riding the light inward. Then, at its closest approach, deep in the gravity well and moving at tremendous speed, it performs an Oberth maneuver, a single powerful burn that flings it up out of the plane. And then it continues riding its sail outward and upward, climbing into the polar regions, finally reaching the vantage point no spacecraft has ever held. The dive provides the kick. The sail provides the patience. It is interesting that the two solutions sit at opposite ends of temperament. The Oberth dive is bold and sudden, a plunge into danger, a single decisive burn at the most extreme moment, everything riding on a few minutes near the fire. The solar sail is the opposite, gentle, slow, almost meditative, gaining its victory not through one dramatic act, but through endless, quiet persistence. Year after year of a feather-light push. One is the sprinter. The other is the marathon walker. And the most likely path forward may be to let them work together. The patience of the sail and the power of the dive combined into a single mission. It is a reminder that there is often more than one way to solve an impossible problem, and that the most stubborn walls sometimes yield not to brute force, but to cleverness and to patience. Together, they could carry us to the one place in our own solar system we have never managed to go directly above or directly below, our star. There is a quiet kind of courage in missions like this. A journey of this sort would not be quick. Spiraling inward on a sail, diving past the sun, climbing out over the pole, it could take many years just to reach the vantage point, and many more to gather the science. The people who first sketch such a mission on paper might be well into the later chapters of their careers before a single image comes home. Some of those who begin the work may hand it on to a younger generation to finish. This is the nature of the deepest space exploration. It runs on patience, measured not in days, but in decades. We saw it with the Voyagers, dreamed up by people who knew the grand tour of the outer planets would unfold across the better part of their working lives. We see it with the long, looping missions that tilt slowly toward the sun's poles, one planetary flyby at a time. It takes a particular faith to start something whose reward you may only glimpse near the very end, to plant a tree, knowing you will sit in its shade, only briefly, if at all. But that is how the hardest frontiers are crossed. Not in a single bold leap, but in a long, patient climb, carried forward by people willing to begin a thing they may not personally see completed. And the view waiting at the end of that climb would be one no human being has ever had. So, let's say we do it. Let's say that some future mission, riding a sail, diving past the sun, or both finally climbs high above the plane and points its instruments back down. What does it actually see up there? The first surprise is that the view itself changes. Physically, the sky gets cleaner. You see, the disk that the planets live in is not empty. It is dusty. Over billions of years, comets have shed material as they swung past the sun, and asteroids have ground against each other in countless collisions, scattering a fine haze of dust all through the plane of the solar system. This dust hangs in a thin sheet, concentrated right along the disk, the same disk Earth travels in. And you can actually see it with your own eyes, if you know when and where to look. On a very dark night, far from city lights, just after the last of the sunset has faded, or just before the first hint of dawn, you can sometimes spot a faint, ghostly cone of light rising up from the horizon. It looks like a soft pyramid of glow, leaning along the path the sun takes through the sky. That glow is called the zodiacal light. And what you are seeing is sunlight reflecting off all that dust scattered through the plane of the solar system. It is, quite literally, the inside of our own disk, lit up. When you look at the zodiacal light, you are looking at the haze we are embedded in. There is even a faint companion glow directly opposite the sun in the night sky, where sunlight bounces straight back off the dust toward us. A soft patch of brightness so subtle that most people will never knowingly see it. Astronomers call it the Gegenschein, a word meaning counterglow. Both of these gentle glows are sunlight scattering off the same vast, thin sheet of dust that fills our plane. The slowly grinding debris of comets and shattered asteroids, smeared all through the disk we travel in. It is a beautiful thing to see. It is also, for certain kinds of science, a curtain we cannot easily pull aside. For anyone standing on Earth, or for any telescope orbiting within the plane, that dust is simply everywhere we look, because we are sitting right inside it. Now, a spacecraft climbing up out of the plane would rise above that dusty sheet within a matter of months, and the view from up there would be dramatically cleaner. Far less scattered light, far less background haze, a darker, clearer sky. That clean vantage point would be extraordinary for certain kinds of astronomy. Think of the lengths astronomers already go to in search of dark, clean skies. They build their great observatories on remote mountaintops, far above the thickest, most turbulent air, away from city lights. They launch telescopes into orbit entirely, to escape the atmosphere that smears and dims the view from the ground. All of it is a battle against the things that get between us and the faint light of the distant universe. A telescope lifted above the plane of the solar system would win one more round in that battle, escaping the haze of our own dust, the soft glow that fills the sky we are embedded in. It would be among the cleanest, darkest places from which a human instrument has ever looked outward. A perch above the dust, in the quiet over the pole, gazing into a sky a little blacker and a little clearer than any we have ever observed from. From above the dust, a telescope could detect faint signals that, from down inside the haze, are simply washed out. It would be one of the finest places imaginable to hunt for the faint glow of planets around other stars, searching for the subtle fingerprints of distant worlds, and perhaps, one day, for signs of life among them. From the same clean perch, other instruments could study the faint afterglow of the early universe, or examine the structure of our own galaxy from a fresh angle, free of the dust that blurs the view from within the plane. It is worth dwelling on just how much that dust costs us. When astronomers try to photograph planets around other stars directly, not just detect them indirectly, but actually capture their faint points of light. One of the great obstacles is right here at home. The glow of our own zodiacal dust, that haze scattered through our plane, adds a soft background brightness to everything we look at. A distant planet around another star is unimaginably faint. Its light has to compete against that local glow, and often loses. Lift a telescope above the dust, into the clean dark over the pole, and that background brightness falls away. Suddenly, the faintest specks become visible. Worlds that were drowned out could emerge. It would be one of the most promising places ever to search the atmospheres of distant planets for the chemical signatures that might hint at life. And the afterglow of the early universe is no less remarkable a target. Spread across the entire sky is a faint hum of radiation left over from the birth of the cosmos itself, the oldest light there is, released when the universe was very young. Studying that ancient light tells us how everything began and how it has grown. But the faint glow of our own galaxy and the dust between us and the deep sky gets in the way. A clean vantage above the plane would help peel those foregrounds apart, letting us read the most ancient signal in existence a little more clearly. The second thing that changes is the environment around the spacecraft itself. Down in the plane, near the sun's equator, a probe sits in that slow, gusty, turbulent solar wind. But climb above the pole, into the path of the fast wind pouring out of the coronal holes, and everything shifts. The spacecraft would find itself in that smoother, faster stream particles flowing outward at hundreds of miles per second in a steadier, cleaner current. A fundamentally different kind of space. That difference is not only of scientific interest, it matters for the spacecraft's own survival. The radiation a probe absorbs, and the particles that batter its electronics, depend on where it sits in the sun's three-dimensional weather. A craft riding through the fast polar stream experiences a different bombardment than one drifting in the gusty wind near the plane. Understanding that environment helps engineers know how long a probe's delicate components might last out there, and how to harden future missions against the conditions they will face. So flying above the pole is not only a way to learn about the sun, it is a way to learn how to build the very spacecraft that will one day explore it more thoroughly. Riding through that polar wind would let instruments study the fast solar wind at its source, sampling it fresh as it leaves the sun. Instead of after, it has churned and mixed its way out to where the planets are. It would teach us how that wind is born, and how it shapes the bubble we all live inside. And there is more that only a journey out of the plane can measure. Cosmic rays do not flood into the solar system evenly. The way they leak in seems to depend on direction, on whether they approach along the plane or down over the poles. From inside the disk, we can only sample them as they reach us here, in our one fixed location. A spacecraft climbing high above the plane could measure how the cosmic ray intensity changes with latitude thicker here, thinner there, and from that, read the three-dimensional structure of how our bubble lets the galaxy in. It is the difference between feeling the rain on your face in one spot and rising into the sky to see the whole shape of the storm. Everything we measure from within the plane is a single point of view on a structure that is fully three-dimensional. To rise above it is to trade that one fixed perspective for something far richer, the chance to see how the sun's influence is arranged, not just around us, but above and below us too. And this matters for more than pure curiosity. As we look towards sending people further out back to the moon for long stays, and onward toward Mars, the radiation streaming from the sun becomes a genuine danger to the crews who will travel through it. A sudden storm from the sun, striking astronauts far from the shelter of Earth, is one of the most serious hazards of deep space travel. To protect them, we need to forecast the sun's violence, to see the storms coming before they arrive, and to understand the machinery that produces them. And that machinery, as we have seen, has its roots at the poles. A clear, sustained view from above could sharpen our forecasts, giving future travelers more warning and a better chance to take cover when the star turns dangerous. So the climb above the plane is not only about satisfying a centuries-old curiosity or filling in the last blank on the map of our solar system. It is also, in a very practical sense, about learning to live alongside our star as we venture further from home than we ever have before. The better we understand the sun from every angle, including the two we have almost never seen, the safer those journeys become. In a sense, the view from above the pole is not just a window onto the sun. It is a window onto our own future among the stars and onto the long road that leads away from home. Every great step outward has begun with a change in how we see. And the next great change in perspective may come from the simplest, most stubborn direction of all, the one straight above our heads, where the top of our star has waited, unseen, since the very beginning. And then there is the third thing, the big one, the view we have never had. From high above the plane, for the first time, you could see the solar system as the disk it truly is. You could look down and see the planets spread out in their flat ring around the sun. You could see the dusty haze hugging the plane. You could begin to trace the great bubble of the heliosphere wrapped around all of it, finally getting a sense of its real shape. Picture what that view might actually look like. The sun, a brilliant point of fire, no longer rising and setting, but simply hanging there, seen from straight above its pole. Around it, the planets strung out in their wide, flat rings. Not a tidy diagram, but the real thing. Each world a tiny lit speck on its own great circle. The faint glow of the dust disk spread thin across the whole plane like a film of haze on still water. And around all of it, almost too faint to see, the vast curved boundary of the bubble holding the dark of the galaxy at bay. Our entire neighborhood laid out flat beneath the spacecraft, the way a city looks from an airplane window, and it could be done from either side. A probe over the North Pole would look down on one face of the disk. A probe under the South Pole would look up at the other. Ideally, we would want both two vantage points, above and below, to see the whole structure in 3 dimensions and watch how it differs top to bottom. For the entire history of our species, we have only ever seen the solar system from the inside, embedded within it, peering outward through the dust along the plane. We have never once looked down on our own cosmic neighborhood from above. Think about what a profound shift that would be. Consider what it did to us when we first saw Earth from space. When the Apollo astronauts looked back and photographed our whole planet hanging in the black, that single blue marble, it changed how an entire generation understood home. A small, fragile world with no visible borders, alone in the dark. That image rearranged something in the human mind. And there was a second image, years later, even humbler. As one of the Voyager spacecraft sailed out past the orbit of Neptune, its camera was turned back toward home for one last look. In that photograph, Earth was not a marble. It was a single dim point of light, barely a pixel, lost in a scattered beam of sunlight, a tiny mote suspended in the vast dark. Everyone who had ever lived, every triumph and every sorrow of all of human history, all of it folded into that one faint speck. That picture, too, changed how we see ourselves. It made our whole world feel at once unbearably small and unspeakably precious. Now, imagine the next version of that picture. Not Earth from orbit. The entire solar system seen from above. The flat ring of planets. The burning star at the center. The faint disk of dust. The great shielding bubble holding back the galaxy. Our whole home, photographed from outside its plane, the way we now routinely photograph Earth from outside its surface. We have never taken that picture. Out of all the breathtaking images we have gathered across the cosmos galaxies, billions of light years away, nebulae, where stars are being born, the rings of Saturn, the surface of Mars, the one photograph still missing is the one looking down on ourselves. The portrait of our own solar system, seen from above. It is, in a strange way, the most local image imaginable and the hardest of all to capture. Everything else we reached by traveling outward, with the current, riding the speed we were born with. This one image requires us to fight that very speed, to climb against the grain of everything, and rise above the only plane we have ever known. And there is something deeply human in wanting that image. We are a species that has always needed to see itself from the outside to understand itself. We climbed mountains to look back on our valleys. We sailed out to sea to glimpse our own coastlines. We rose into the sky and finally saw our cities, our rivers, our whole planet laid out below. Every time we have managed to step back and look at where we live from a little further away, something in us has shifted, a new humility, a new sense of scale, a new tenderness for the fragile place we call home. To rise above the plane of the solar system and look down on the disk would be the next step in that long tradition. Not just a scientific achievement, but a change in perspective, a chance to see our entire neighborhood the way we have learned to see our planet, as one small, ordered, precious thing adrift in a much larger dark. It is the kind of view that does not just teach us facts. It rearranges how we feel about our place in things. So that is the answer to the question we started with. What is directly above and below the sun? The honest reply is that we are only just beginning to find out. Above the disk and below it lie two columns of space that should have been the easiest places to reach, and instead turned out to be among the hardest, locked away from us, not by distance, but by the enormous sideways speed we carry simply for being part of this spinning system. Up there is the cleaner sky, above the haze of our own dust. Up there is the fast wind, pouring out of the open magnetic chimneys at the poles. Up there is the vantage point from which the tangled engine of the sun's magnetic cycle finally reveals itself, and from which the true shape of our great protective bubble could at last be seen. And up there, waiting to be taken, is the one photograph we have never managed our entire solar system, viewed from outside its plane. The disk and the star and the bubble, all laid out below. We have flown to the edge of the planets. We have touched the atmosphere of our own star. We have crossed the very boundary of the bubble and slipped into the space between the stars. But to simply look down on where we live, to rise straight up and gaze back at home, we are still planning, still dreaming, still working out how to fall toward the fire in order to be flung above it. Somewhere in the years ahead, a spacecraft will make that climb. It will dive toward the sun, fire its engine at the bottom of the fall, spread its sail to the light, and rise into the empty heights above the pole that no machine has ever occupied. And when it turns its camera around and sends the image home, we will see our solar system whole, from above, for the very first time. A small, flat disk of worlds. A single star at the center, and all of it wrapped in a fragile bubble, drifting quietly through the dark of the galaxy. The direction we never go will finally have been gone, and the last great blank space in our own backyard will, at last, be filled in. Thank you for spending this time looking up and out and over with me tonight. If this journey gave you a new way to picture the place we call home, a like or a subscribe would mean a great deal, and it helps these explorations reach more curious minds. Until next time, keep looking up. There is always another frontier waiting just above the one we know. Good night.